Hi everyone, welcome to another ZX seminar. And today we have Rafael Haenel, I hope I pronounced that correctly, sorry, who will be presenting to us about their new tool from QEra, the tsim, a fast universal quantum simulator. So please, Rafael, if you want to get started.
Yeah, thanks for having us. And yeah, we're excited to kind of tell you about this new project we developed and just recently put open source a couple of weeks ago. A new simulator called tsim, which is based on the ZX calculus and much of the work that's been previously done in the community. And so really this is a simulator targeted towards quantum error correction. So I thought I'll start with a mini overview of QEC. Um, in quantum error correction, our aim is to encode quantum info or protect quantum information by introducing redundancies through a quantum error correction code. And codes always have these three parameters that you'll see a lot, NKD. It really tells us that we try to encode the quantum information of k logical qubits into a larger Hilbert space spanned by n physical qubits. And a code always has a distance, which is a measure of its error correcting power, that tells us how many individual Pauli operations do we have to apply to convert one logical state into another state without really being able to notice by the checks of the code. And the maybe most famous example is the surface code, which is a grid of qubits, of physical qubits. Um, and what we do is we continuously measure these so-called stabilizers. So we continuously perform a certain parity check measurements, either checking the bit flip parity or the phase flip parity. And if a general error occurs somewhere on my qubits, then these parity check measurements will project those errors down into Pauli errors. And the presence of these Pauli errors will have a signature, and the signature will be flips of some of these stabilizer or parity check measurements. So these are the so-called syndromes. So given information about these checks that we measure, whether they've been flipped, we can kind of infer where errors have occurred and correct for those errors. And the logical information itself is encoded non-locally throughout my qubits. So in order, for example, to access my logical X information, measure my logical qubit, the X operator of my logical qubit, I have to perform these non-local measurements of a string of Pauli operators. Same for the Z basis. And these codes can have a lot of qubits, so the qubit count can grow a lot, depending on the distance. So we have a D by D grid for a distance D code. Um, yeah, so that's kind of a mini overview of some QEC code, just so you have an idea what types of operations are involved. And yes, importantly, the number of qubits in QEC can be quite large. Now, most of these, or virtually all of these QEC protocols have first been proposed in theory. And now we're kind of in this exciting time where more and more complex and sophisticated protocols can be executed on hardware. But still, kind of progress is dominated a lot by our ability to simulate these kinds of protocols. So having good simulators is really important, really important for the field. And so an important question to ask is what types of requirements such a simulator must satisfy. And so we've kind of nailed them down into three main ingredients. First, you want to ask what types of circuits do you actually need to simulate? And in QC, we're interested of simulating on the gadget level. We don't really need to simulate full logically encoded quantum algorithms, but it's sufficient to take out certain kind of certain gadgets, certain substructures, and simulate them to extract their fidelity. For example, you might be interested to just simulate that stabilizer extraction protocol before, and in that would just be a Clifford circuit, because yeah, most of the gates in QC circuits are just Clifford circuits. Or you might be interested in simulating some state preparation protocols like magic state protocols. And these circuits tend to be of low, meaning they have gates. So they're mostly Clifford and have few T. Um, you need to do in order to compute some fidelities. You actually need to simulate these circuits under realistic noise models. And one of the go-to model is to put Pauli errors into your circuit. So you after every gate, you also inject some Pauli channels that are kind of representative of what is going on some actual quantum hardware. Often they're obtained using a Pauli trolling approximation from some more realistic noise channels. But Pauli errors turn out to be quite nice to simulate. So a lot of the quantum error correction literature actually just focuses on these Pauli errors. And of course, there's much work also on other error mechanisms. But kind of, well, one main avenue is to simulate Pauli errors. And then finally, you need to run a lot of simulations. You usually perform extensive Monte Carlo sampling. And that's because if your circuit has good error suppression capabilities, for example, has a logical error rate of 10 to the minus 9, then you have to run the circuit a billion times in order to get that one shot where it failed and where you were not able to correct any errors. So these QEC type simulations, you have large circuits. You don't just want to simulate them, be able to simulate them or be able to simulate them a few times, but you need to simulate them fast to generate lots of samples from the statistical distribution of your circuit. So yeah, these are the three categories. We have low magic circuits, Pauli noise, and we need a lot of shots. And then we want to show you how tsim addresses all of these key three requirements using various techniques in the ZX calculus. So in order to simulate low magic circuits, we use stabilizer rank decomposition, framed in the language of ZX calculus. In order to represent Pauli noise channels, we actually use a parametric version of the ZX calculus. Well, the ZX calculus himself is parametric, but techniques introduced by Matthew Sutcliffe, who's also in the talk right now. So based on his work, we're using an extension of physics that makes use of parametric rewrite rules, where we model Pauli noise as parametric Pauli vertices in the ZX diagram. And also building on Matthew's work, we're able to achieve quite fast throughput, quite high throughput by exploiting parallelism across these many different shots that we all want to generate. So that's one key aspect. You have a very nice parallelization dimension. Don't parallelize about kind of any parts in your simulation itself, but parallelize across the different shots that you need to generate. And so that's kind of the basic overview. And I'm just going to jump into a demo and explain some of the things about tsim by running it in a notebook.
Sorry, could you zoom in a little bit more on the text? It's a bit small now to see.
Oh yeah. Do you think this is better?
Yeah, that's better. Thanks.
Okay. So there's various ways to program quantum circuits for tsim. At Quera, we have our own compiler tool chain and circuit level languages to describe quantum circuits. So what you could do, you could write a Squin kernel if you wanted to use Quera's framework. So you just define a main function that you decorate with this as a Squin kernel, and then you can write the instructions of your quantum circuit and make use of structured control flow and other nice features. So you just define your quantum circuit in some way, and then you convert that into a tsim circuit. And then there's various tools to visualize the circuit. And in fact, tsim is heavily using stim, and I hope people are mostly familiar with stim, and I think there has been a ZX seminar on stim as well. So if you're familiar with stim, then you'll find that tsim is really easy to use because almost everything is basically the same, but it'll support non-Clifford circuits. So you convert it into this tsim circuit object, and so now you can see your circuit right here. So there's a T gate. We're kind of creating this correlated state. And then there's some depolarizing Pauli noise channels right here. We're measuring a parity, and then based on that measurement, we're actually performing performing a bit correction and then measuring those qubits as well. And the workflow in tsim, just like in stim, is you have your circuit and then you compile it into a sampler. That's a one-time step that might take a while. And after that, you can efficiently generate many shots of the circuit. So for example, now I'm asking it to generate 1 million shots of the circuit, and that can be quite fast. I mean, it's a small circuit, but in general, it can be quite fast. And so what it will return back to you is this NumPy array of 1 million rows and 3 columns, where each column corresponds to one measurement gate in your circuit. And so the inner workings of tsim is based largely on this work by Matthew, on where the concept is to express everything as a ZX diagram and then compile that into a contiguous data structure that's efficient for evaluation on CPU and GPU. So we can kind of see the ZX part of it if we plot the circuit in a different way. So you can call the diagram method and ask it to use physics for plotting. And
Rafael, can I ask a question?
for sure.
So you're saying that for every circuit, you made it a sampler, and what is the information in the sampler? Is it the noise that you plug in, like using the noise channel that you just presented?
Yeah, so the sampler, it knows, well, it's basically everything that's in your circuit. So it just converts the circuit into all the information in your circuit. So which gates are applied. And I'll talk a bit more about these Pauli channels, right? So this is the noise model, right? So this is a depolarizing channel where I just said, so this is the statement here, with 50% do nothing, and with 50% either do an X, Y, or Z gate. So that's kind of these are the probabilistic Pauli channels, so probabilistically applied Pauli vertices that are encode in here. So that's all the information that you use to construct your circuit, and all of that is compiled into your sampler.
So can I understand that at every shot, you randomly toss a die, and this die tells you, oh, at this Pauli channel, I would use a Y arrow or X arrow or Z arrow or no arrow.
Exactly. Yeah, that's how you can think this. Yeah. So yeah, you toss your die and you put some actual Paulis in here or nothing in here. Exactly. And then you have a specific noise configuration for your circuit, and that will lead to different measurement bits. Yes. And you do that a million times. Yeah. If you ask it to do, but then it'll toss the die a million times and give you all these bits for different noise configurations. You don't have to put noise in, right? I mean, everything will work if you just like if you just disable this one, right? And you can still sample it, and then the output will just follow the distribution of your quantum circuit without noise. But yeah, you can put noise in and you can put no noise in. Yeah. Good question. Okay. So your circuit internally is represented as a ZX diagram, and you can see it by calling the diagram method with a physics argument. And actually for this visualization, we're making use of this doubled notation of the ZX calculus. So you will see that different to maybe physics, all these lines are now in bold. Just measurement gates do not have bold lines.
Sorry, is this different now? Like, is this a recent addition?
Yeah, so yeah, I mean, I should say the current release does not have this visualization method. It's using it under the hood, but we'll, yeah, I'm kind of showcasing something that's soon to be released in the next follow-up version. Yeah,
I see. Okay,
that's a
thank you.
good disclaimer to add. Yeah, if you try it right now, you won't quite see it that way, but soon you'll see this doubled notation of the ZX calculus also in the physics D3 visualization.
So would there be backwards compatibility if there's code written in the older notation, for example?
No, it's just the visualization that's changing.
I see.
Everything else, nothing else is changing. Yeah,
I see.
everything else
Okay,
is,
thank you.
at least for now. Yeah, yeah. Yeah. So the doubled notation, So that's useful if you want to represent measurements and traces. So if you're familiar with this, whenever I draw something in bold, I have to double everything and conjugate phases. And that's equivalent to, if you think about a density matrix, how that is kind of doubled of a bracket and psi, bra and ket of psi. So you have psi and its conjugated version making up the density matrix. So you want to double everything. And measurements are represented by spiders that are not bold. And you can have additional legs that kind of track your classical information coming from here. And I think one nice way to think is, well, what is a measurement doing? It's projecting either to the 0 pi state. So if you decompose your diagram like this, then you exactly see that, right? So either you project down to 0 state, and you can track your projection you did here, or you project down to the pi state. And if you want to represent a trace, right, that is equivalent to doing a measurement and not tracking the outcome. So you see that here, and if you follow the rule, then you kind of just see you connect two wires, you trace out two wires, and you doubled ZX diagram. So yeah, that's what you see here. So your measurements are just vertices that are not bold, that kind of connect your two halves of the doubled diagram. And a second way to insert circuits into tsim is just using the stim format. So if you're familiar with stim, you would also do it that way. You can just encode your quantum circuit as a text string. So if you write C0 between 0 and 1, you'll get a C0 gate. You'll see that here. And now you can see a measurement is just this one. You can have a reset gate, for example, that would first measure and not record, right? So we'll just trace out your qubit and then reinitialize it in the 0 state. But you can also do more advanced things. Basically, everything that's supported in STIM itself is also supported in tsim. You can also do something like this. You could say measure qubit 0 and record the flip bit, and then do a classically controlled C0 based on that most recently recorded classical bit. So if you represent that using a ZX diagram, this is how it would look like. And you can kind of see this classical control is just doing a C0 essentially based on that classical measurement outcome that was previously flipped, because we had that flip operator here. So if you're familiar with STIM, then this will feel very natural. Otherwise, it's also very easy to get used to. And then importantly, noise. So noise, we said, is the presence or absence of a poly vertex, and that's modeled as a parametrized vertex in the diagram. So if I have an X error, I just put a X spider in here, and the phase I leave as parametrized, where these variables right here should be seen as binary variables, indicating that the phase is either 0 or pi. So this way, I don't have to build new ZX diagram for every noise configuration, but I just build a parametrized diagram once, and that captures all noise configurations. So for example, if I turn this into Y, I would need a green and a red spider, and both should have the same bit, right? So because I should either have X and Z present or just nothing present. And this would be a Z error, just a Z spider parametrized. Or I could have this depolarized 2 instruction, where I would actually need four bits, because for depolarization gates, I could have X, Y, Z channels or nothing. So if I wanted to have a Z channel, I should set E0 and E1 to 1 to a phase pi. Sorry, if I wanted to have a Y channel, I should set both of these bits to 1, for example, and we'll get that here. And depolarized is called a depolarized 2 channel because it kind of correlates across two different qubits. So I just need to put in these vertices in my diagram, and then kind of track the probability distribution that governs these binary variables right here. That's how I incorporate noise in the ZX diagram. And now here comes another important aspect. If you're familiar with stim, there's this concept of detectors. For QC experiments, often we don't just want the measurements themselves, but we're more interested in certain XOR combinations of these measurements, and we refer to them as detectors. So we just want to transform our bits using some XOR operations into some new bits that we call detectors, and that are more useful for us to talk about. And of course, in a ZX calculus, there's this nice representation of the XOR gate using a red spider like this. So I can build a circuit like that here. So I'm just creating a Bell state, measuring it, and then I'm building a detector, which is the parity of the two most recent measurements that I always access, like in stim, using this rec -1, like the most recent and the second most recent measurement. And so this is how in a ZX diagram. So you can see I have my two measurements, and then I perform an XOR operation to get my detection bit out of here. And then so this is how I define my circuit. This is the corresponding ZX diagram. Now there's two modes that you can do. You can either compile a sampler, and the sampler will just sample, it will ignore the detectors completely, just like in stim, and just sample your measurement bits. In that case, you'll see that you get either both true or both false with 50% probability because it's a Bell state. Or I can compile a detector sampler. This one will not return you the measurement bits, but will only return you the outcomes of this detection bit. And so it will, in this case, return you the parity of those two measurements. And so that should always be odd, right? But because both of them are 0 or both of them are 1. Yeah, so that's the concept of detectors in tsim, same as in stim. If there's any questions, maybe now is a good point to ask.
Yeah, maybe this is jumping the gun a bit, but usually detectors are things you post-select on, right? So then if you're doing the first type of sampling you showed there, is that sort of the version where you post-select on the detector giving you 0?
I mean, I could, if I wanted to post-select, right, I could just take these samples, and then like get a, I don't know, mask is where a sample. Well, actually, let's call these detectors. Mask is like detectors is equal to 0, right? So I can do now, right? I now have my detection bits, and based on that, I will filter my data out. Oh, I'm saying I only want to retain shots where my detectors were 0. So
But here you only generated samples for the detectors, but then you want to generate samples for both the outcome bits and the detectors at the same time, and use the mask, right?
Yeah, so actually, yeah, there's detectors, and then there's also observables. These are so you would generate two types, and we'll see that later on. Detectors and observables, they're both XOR combinations, just that they have different meaning of your measurements, just that they have different meanings. Yeah, so usually the observables are just the logical bit, right? You just convert your physical bits into your logical information, and then you can post-select, right, the logical bits, only keep shots. So you have all your shots that has the detector and observable data. You post-select all of these shots based on detectors being all 0, for example, and then you only look at these post-selected observables, for example, to compute your expectation values. Yeah, but it's all just something you would do yourself manually in post-processing. Yeah.
Yeah, just a comment. So, by detector, it's not just used as post-selection. It can also be used for error correction. So basically, you can, based on the detector measurement result, to infer what error happened during the circuit, then correct your logical measurement result. So in that way, you can do error correction.
Oh, sorry. What happens if your detector has error? Like, for example, when you have that classical bit, how do you know that one is always correct? What if there's a bit flip?
That's a good question. So basically, in conventional quantum error correction, the way to detect the measurement error or the stabilizer flipped error is that we measure the stabilizer, the same stabilizer for repeatedly for several times, so that you can use the, for example, majority vote to get the reliable measurement results.
Thank you.
I see there's raised hands from some other people. I see Quark has raised hands.
Hi. I just want to ask if there are like a bit like functionalities to just sample for the like a zero, like a trivial detector value. So like in some post-selector protocol, like you don't, like you just want to, like as soon as one detector returns zero, you just want to throw away the well, sorry, as soon as a detector not return a zero, like out of I don't know how many detectors, you just want to throw away that shot. Is there innate ability to do that now? Like,
Yeah, not yet, but that's a really good point. We're planning it, or maybe someone wants to implement this. That would definitely be a huge improvement for many QEC workflows. And yeah, there can be some huge benefits of kind of having some post-selection integrated into the API as opposed to kind of generating all samples and post-selecting after. Yeah, so that's something that will be there at some point. Yeah, or maybe someone wants to implement it. Yeah, good point.
okay, thank you.
Oh, I see Andre has a raised hand.
Hi, I'm sorry if you've already addressed this and I missed it, but am I correct that these detectors still only work with um, sort of expected outcomes? Like if everything were noise free, then the detector would necessarily return that there is no fault. In particular, I'm wondering, is there a way that one can wire the detector through a non-Clifford gate? Like
Yeah,
include a detecting region, like where the detecting region includes some non-Clifford gates that don't commute with the detecting region.
yeah. So for all that tsim is concerned, detectors are really just XORs of measurements. So it doesn't matter if there's T gates or non-Clifford gates in there. Of course, if you want to interpret these detectors, then it matters if there's T gates, right? That would somehow affect your detection region. But that one really doesn't affect tsim because it just computes the bit values corresponding these detectors, and those are just XORs of measurements. So tsim doesn't give you any tools of computing detection regions, for
I see.
example.
And presumably it will still yell at you if you have like non-commuting detectors, right?
Yeah,
Okay,
it
cool.
doesn't. Yeah, but maybe that's some checks that we could insert. Yeah, actually, currently, and I should also say tsim is a fairly early version, right? We built this fairly recently and released it just a couple weeks ago. Yeah, it doesn't yell at you like stim. Yeah. Okay. Yeah. So the first mode is the detector sampler, and then there's the regular sampler, and then there's a detector sampler. And now here's one more example of a slightly more complicated circuit. I'm just going to run this. And so this is how this circuit looks like. And so these are actually two patches of repetition codes that I initialize the first repetition code in a T state and then do a transversal C naught on them. And so if I look at the same circuit in as a ZX diagram, then this is how it looks like. Note that I have these measurements and then I have detectors and I also have observables. And so this is how it looks like as a ZX diagram. So detectors have kind of this nice form, right? I just explicitly see the XOR gates, right? So this detector is just perfectly equivalent to that measurement outcome. But then I have one detector right here is checking the parity between two subsequent rounds. That would be my detector 2. And then here I have a logical observable that just corresponds to this particular measurement bit, for example. And yeah, measurements you always recognize. I guess we put this label on top, right? But they're biters that are not doubled, they're not bold. And here would be a reset gate, for example. And you can see some bit flip errors inserted in here, right? So all of these X vertices with phases with parameters E0 are just X error channels. And so what I can do now, I can go ahead and full reduce this diagram, and I'll find that it assumes a much simpler form. And Chen will go in more detail about this, but for Clifford circuits, whenever you build one of these QEC circuits and hit ZX full reduce, it'll essentially separate your circuit, factor it into your detector parts and your logical circuit. So this one is the logical circuit of 2 bits because I had 2 code patches, each with 1 logical qubit. So you get this connected component of just two outputs, and then here are your detectors. So the ZX calculus can be a very nice representation of like separating the kind of detectors from the observables, and they're still correlated through these variables right here, these F variables. I haven't really said what they are, but if I set this to false right here, then you kind of see that, yeah, these vertices right here are given in terms of the initial error channel variables right here. So you still have correlations between your detectors and your observables, but they're all captured kind of as these classical Pauli correlations right here. And yeah, so I'll leave it here, and Chen will give some more detail about this. So with tsim, you can do basically anything that stim does, and it can be quite performant. So stim has these features of generating some example QEC circuits. For example, here's a surface code circuit of 7 rounds with distance 7. So if I plot this, and here I'm just building a stim circuit in stim, and then I can just say convert this to tsim using from stim program, and now I have a tsim circuit. And if I plot this, so this is a surface code memory experiment. You have these different visualization methods for that, right? So it's this quite long circuit, and now I can also represent this as a ZX diagram, right? That's what it become. The representation is maybe a bit not quite as useful, right? Because it's a pretty large diagram, and you can see all your detectors. So yeah, maybe one could improve on the presentation here. So I'm just not gonna show this. And so it can be quite performant, especially for the Clifford case. So here I'm just sampling it a number of times, actually like about 64 million times. And I see that I get a time of just 4 nanoseconds per shot to sample from the circuit. In this case, it's actually faster than stim. So here I'm doing the same with stim. So I'm using the stim sampler from the stim circuit above. And if I run this, stim is so we're outperforming stim in this case, yeah. Now this is take this with a caveat, because this is for Clifford circuit, so we don't have to do very much work in this case. It'll not always be the case, but in some cases, you can outperform stim using T.
Sorry, Rafael, I'm a bit confused by that because stim is specifically meant to be as performant as possible on Clifford circuits. And here you're saying that on this purely Clifford circuit, you're 100 times faster than stim.
Yeah.
How is that possible?
Yeah, yeah, we can go into more detail, but the problem is actually quite easy because you have such a you get these very simple ZX diagrams. The problem just reduces to really sampling your error variables E, and then building linear combinations out of them according to this part of the diagram, which mirrors your detector error model. And STIM actually doesn't make use of this optimization. STIM actually samples measurements directly and builds XORs. So yeah, if you just compute this graph using ZX, then you can be more performant than that because there's some optimization stim doesn't make. Yeah.
Okay. That's very cool then.
Yeah,
Sorry,
but it's not. Yeah,
did you include the time of computing that graph in this?
I did not. Yeah, stim is much faster at that initial step. Well, because tsim is all Python. It's 100% written in Python, and it's based on physics. And so that initial, but it's a one-time initial cost, right? So yes, tsim will be significantly slower, but you do that once, right? And then you sample millions or billions of time, right? So in the limit of many samples, that one-time cost doesn't matter. Yeah.
Assuming the cost isn't too high, but yes.
Assuming it's not too high, yeah. And one can think of improving it by moving to Quizzix at some point, yeah. Yeah.
And can I think of like this decomposition of using ZX or PhysiX as a pre-processing of your circuit? So you basically you do it and once for all, and the more shots you're doing, the more saving you gain from this pre-processing.
Yeah, absolutely. Yeah. Yeah.
And have you noticed like any bottleneck for this? Like, or you so far for all the samples or like sampling circuit that you run, they all give you very efficient decomposition.
It really depends on, yeah, it really depends on the circuit that you're running, yeah. We'll see a bit more when, yeah, I'll give you a few more examples later on.
Thank you.
To give you a bit of a feel. Yeah. And I also, yeah, this is kind of a maybe stark example. It's not always that good. So it is really fast because we are doing sparse sampling of these random variables, and I chose a pretty low error rate. So even if I increase this, so um and this is all Python currently, right? And so if I increase this and run this again, then we should see that it becomes quite a bit slower. So there's regimes where you can be faster than stim, but not always.
Are you doing the geometric skip sampling now, or is it?
Yes, yeah, we're doing that, and that was
I
actually a
see.
suggestion by you, yeah. So that's done in this case, yeah.
Okay, nice. So it's all implemented in tsim now.
Yeah, I think it's in the main branch now.
Okay, great, lovely. Thank you.
Actually, I should have reduced. Yeah, so now we're slower than stim, right? If we do that. So it depends. Take it with a grain of salt. So stim brings this sinter tool, which is a tool to do Monte Carlo simulations, and tsim is technically fully compatible with that. So I'm not going to go through the code here, but here I'm just running a typical QEC simulation, and I'm doing everything using tsim. So I can run this, and within a few seconds, using kind of the boilerplate code that's pretty common in QEC workflows, I can generate these QEC Monte Carlo simulation plots. Like this of computing the logical error rate versus the physical error rate. So you can use some tools that are available. You can use them. And now the last part is the important part. These are the non-Clifford circuits. So here I have a magic state distillation circuit, and this is actually something that was run on Quera's hardware about a year ago, and there's a Nature paper about it. And so that used to be fairly hard to simulate, and that's a circuit of 85 qubits, and it has not many T gates, but a few. So if you zoom in, you see there are some rotation gates and T gates, and then the rest is just a Clifford part. And and if I draw this as a diagram and apply ZX full reduce, then you see that it always has this nice structure of separating out my detectors from the logical part of the circuit. So the problem, this complicated circuit, it reduces to a much simpler problem, which I then can start simulating using tsim, and that's an 85 qubit circuit, right? So a state vector simulator would not be able to do this, but we can generate 50,000 samples in just about a second here. And this is on CPU, just running locally on my CPU here. If if I have a GPU connected, then this time would go down significantly to about 600 nanoseconds per shot from this 85 qubit circuit. And yeah, for reference, if I just simulate the circuit using stim, where I don't have any T gates, right? Stim only supports Clifford gates. So if I take that circuit and just remove all the non-Clifford gates, then a stim would give me also about 600 nanoseconds would give you 600 nanoseconds per shot. I'm at 20 microseconds. So we're not that far behind stim is what I want to say. It can be quite performant depending on the circuit.
Rafael, I have a question about the logical error rate that you demonstrated. Why, sorry, not logical, the physical error rate. Why, when you increase it from 10 to the power of -6 to 10 to the power of -4, the efficiency of your simulation is slowed down?
Yeah, and that's because the way we sample these random numbers. Yeah, naively, you would just go ahead and for every one of those Pauli channels, you would like get a random number and then based on that put in an X or Y or Z gate, right?
Mhm.
But for low error rates, it actually makes sense to actually use a geometric distribution because most of these channels will be zero. They will just be identity gates. So in that case, it makes sense to take a geometric distribution and tell you kind of, oh, how many of these will all be zero, right? Right? How many of these channels will all be zero and then go to the next one that is non-zero and put a Pauli gate in there. So that's kind of the sparse way of sampling these random numbers, and that's why it scales in p. It scales as p, the probability of 1 bits basically. Yeah.
Thank
So
you.
that's the reason behind it. So we're doing it sparse, and that allows us to do it pretty efficiently. Yeah, good question. And so now I'll show one more circuit, this magic state cultivation circuit, that has been of high interest in the QC community. And here I'm showing the smaller version of it. This is from work by Craig Gidney. You have these circuits, and you can kind of see your red error channels in there. And also here you see that pretty good it factorizes the ZX diagram factorizes into easier and harder parts. And if I run this, right, compilation will take a few seconds. It is a harder circuit. It has more T gates in this case, but it will eventually compile. And once you run this, I find I get around 6 milliseconds per shot. On GPU, I think I got 100 microseconds. And I guess what I wanted to mention about here, and I'll go a bit more in detail about this, and there will be a whole separate ZX seminar by Quoc. They have our, yeah, tsim is not the end yet. So there have been lots of improvements already, and there can be lots of improvements. For example, this very circuit, Quoc was able to significantly increase the throughput down to just a microsecond per shot on here. So yeah, that was kind of a demo of tsim. How to work with it and kind of some thoughts about its performance. Now I'll hand over to Chen to give a more detail on theory behind it. But maybe if there's any more questions before I'm happy to answer.
Yeah, I have a question. So, is this just out of like theoretical research interest that you implement this framework, or QEra is using this for very interesting experiments?
Well, definitely we're also using this internally for research projects. But the idea is also that our hardware is reaching the point where it is very difficult to classically simulate it with currently available tools. And that makes it harder to use the product, right? The quantum computer, right? Because maybe you want to test your algorithms before you run it on the machine. Shots are quite expensive. So we're also thinking this is a good tool to go alongside with our hardware, for at least for some certain types of circuits QEC circuits that are low in magic, that have few non-Clifford gates. So yeah, I think it's a product generally interested for research, right? And of course, everyone, including us, everyone benefits if there's more progress. But it's also kind of a tool that goes along with our hardware.
Cool. And what magnitude of physical error rate do you assume when you're running this simulation?
Well, that really depends. Yeah. So if you use our software, our blockade software, there is some error models integrated in it. And so we will give you circuits back that have all these poly channels. We have a whole compilation pipeline that basically will go ahead and kind of make its best effort to estimate what these probabilities are, given all the processes happening on the hardware. So it really depends on the hardware, what the probabilities are that you inject, that you put in there. Yeah, and so we are offering something, but you can, I guess, also different papers make different assumptions, and different hardware companies have different assumptions. Yeah.
Thank you.
Yeah, just for your reference, so typically for idealized quantum error simulation, the physical error rate is 10 to the minus 4 to 10 to the minus 3. But for near-term hardware, for example, the magic state distillation circuit we run on the Gemini machine last year, the gate fidelity, 2-qubit gate effective fidelity is about 99.4 to 99.5, so 0.5% error rate.
Thank you.
Hi, sorry, I have a question. Thank you for building tsim, by the way. I actually just noticed it a few days ago, and I'm actually considering it, integrating it into TQEC. I really appreciate the engineering effort of making it a nice package and integrating with Steam and Sinter's interfaces. My first question is, so I saw Craig commenting on Cyrate once that enrolling the Steam circuit leads to some performance overheads, and tsim has to enroll the repeat blocks. Is there a difficulty behind this?
Oh, to inline the repeat statements to flatten
Yeah,
any loops? Yeah, I haven't personally thought much about this. I wouldn't know how to represent repeat statements in ZX diagrams.
I see. So it's kind of a limitation from the physics side.
Yeah, or from my understanding side, and maybe someone has ideas and would like to collaborate and think about this. Yeah, I mean, definitely tsim is more designed for smaller circuits. Stim will scale much better in principle, because tsim is, if you just have Clifford circuits, you should always still use stim. But if you have a few non-Cliffords, and usually these circuits are a bit smaller, then tsim is a good choice. So the repeat statement hasn't been really so important for us because, yeah, because of the presence of T-gates, you can scale to very large circuits anyways. But yeah, you're right. It's definitely a limitation, and maybe one can think about this. Thanks.
So on that topic, if I don't have any T-gates in my circuit, but I do want to simulate or track the parity of some non-deterministic observables, would tsim be scalable enough for a large circuit?
Oh, I see. You want to use it for Cliffords, but allow for non-deterministic observables. I mean,
Yeah,
in
because
STIM,
Steam doesn't support that.
but in STIM, you can always convert your observables to detectors and then allow gauge detectors. And then, so that's a workaround, and it'll work in STIM. So you should just do that.
I see. I didn't know that. Okay. Another question is, would it be easy for tsim to support dynamic circuits? So say here you have this T cultivation circuit, but it's inherently a repeat into success protocol. So say, can you do a post selection on it?
Yeah,
Like
so
if I have some conditional operations in my circuit, would it be
yeah,
easy to support it?
so not easy, no, and maybe not feasible. So yeah, the compilation process of compiling it into a sampler It assumes a static circuit, just like stim does.
Hmm.
And so that's where the performance is coming from this step, right? Otherwise, you
Hmm.
could always construct a separate ZX diagram for every shot, right? And then you would have most flexibility, kind of just like Stim's Tableau simulator as opposed to the flip simulator. Um,
Hmm.
but yeah, so this step is crucial for performance, but it also removes flexibility, just like it happens in Stim. Now you can have controlled Clifford gates in there. But those become non-Cliff, right? If you do a controlled S, that's actually a non-Clifford gate, right? So you can kind of build some more interesting control flow into your circuits, but they come at a cost of being non-Clifford instructions and exponentially increasing the runtime of your circuit. So a bit of this can be tolerated, but not much.
I see, I see. That's what I expected. Thank you.
Thank you.
Hi, I just wanted to ask if you had looked into like different ways of representing these detectors in the ZX diagram, like language. Because so, for example, like if you look at the sort of simplified graph, like at least an issue I well we had was that it was very hard to find cutting when you do have these sort of like for example, like a really long observable would span many different nodes, and we found that it was hard to find a good like cutting decomposition for like when you include these things, right? Like it like at least in our original paper, we're able to get to like maybe like 4 terms even if we don't have these sort of longer detect. I always wondered if you can sort of snip it, do some stabilizer decomposition, and then add it back in some like clever way. Yeah, I wonder if there's a better way of doing it in that sense. Yeah, if I'm making any sense.
Yeah, that's really interesting. I personally haven't thought about this. I mean, the representation is just an XOR gate in ZX, right? So I think that one is unique. Of course, you could choose different detectors, but I mean, that's also a QC problem in itself, right? If you have different if you have different bases
But
of
so,
detectors.
so is it better to X not do the XOR in the ZX LAN and then just set every detector to be some other thing? Like don't do the XOR, just put every measurement as a detector or whatever for that purpose, and then do the XOR outside for post selection. Because there might be better cutting, like there
Uh-huh.
might be better decompositions that way. At least that was one issue that I had when you have all these like like these sort of Pauli product measurements scattered all across the in the cultivation circuits, for example.
I mean, one thing, right, you can do that. You can just not do this graph, right? So this is in the case for your circuit, right? For the magic state cultivation circuit. You could also not have any detectors and just do the measurements.
I see.
I guess now you get this one. So maybe the graph doesn't look as nice, right? Because now you have way more
Ah,
outputs in this connected
I see.
component. But
I see.
maybe cutting works better. I don't know. Yeah, that's a really, really good.
Okay. Oh, I didn't know about this. Okay. Thank you. Yeah, let me.
Yeah,
Yeah.
So
thank you.
I have a naive question about this. Usually when we talk about detector, we are in the context of error correcting code. So if you think of a code that already have a lot of symmetry, then maybe you can do smarter ways of finding this XOR term. Um, but when you're presenting just now, it feels like you're just doing it out of a context. You don't consider error correcting codes. Um, is it just like you're considering a general way to do this, or like there's a particular reason that you just don't think of this in context?
Chen, do you have an answer to this?
I guess here we are just using the ZX component to represent the circuit we want to simulate. In that case, we can represent anything if XOR is required, not specific to quantum error correction, but in quantum error correction, that's what we need. I'm not sure if I answer your questions.
And at what stage of this pipeline do you consider a particular error correcting code? Or you don't consider this?
Well, the code will define
basically
how you
you.
write your circuit. Uh,
Sorry,
so I
what?
guess so tsim or just like stim, it doesn't really know about any code. Really, it's on a lower level. Tsim, it's just like stim, only knows about circuits. So what code you choose will define the circuit that you write. And tsim doesn't give you any help with that whatsoever, just like stim doesn't help you with that. So yeah, you choose a code and then you write a circuit and then you put that circuit into stim or tsim.
Oh, I see. And so for example, like I could think of like that code block as the encoder of a stim code. And then that corresponds to like the isometry that we have for the Cliff stim code encoder.
Yes.
Then if you already know what code you're using, is there a way or informed way for you to decide how do you choose detector for your circuit?
Oh, and detectors, the user has to choose them also individually. You have to do it yourself. tsim also, yeah, maybe I'm misunderstanding, but yeah, you know what code you're using, so you write the circuit, and you know what code you're using, so you also put in these detectors. Yeah, so tsim doesn't choose them for you. You have to put them manually, just like you manually specify the circuit.
Oh, okay.
So on this Go, there's TQECD, a package inside the TQEC community that finds detectors automatically for a circuit without any detector annotations. An advertisement.
Cool.
Perfect.
Thanks.
So I'm gonna hand over to Chen now.
Okay, thank you, Rafael, for the demo and introduction. So basically, I want to talk a little bit more details about the theory behind the box of the simulator. So basically, I will summarize all of the previous simulator we use commonly in quantum or quantum algorithm or quantum computing. So basically, I will characterize the simulator in three different measures: the universality, accuracy, and scalability, where the universality basically characterize if this simulator supports simulating arbitrary quantum circuit, and the accuracy is that whether this simulator give you exact or just approximate a simulation result. And the scalability is about how many qubits you can simulate using the simulator. And can you go to the others? Okay, so for the commonly used, the state vector simulator is a exact simulator for arbitrary quantum circuit, but as a matter of fact, it only supports less than 30 qubits. And it will scale exponentially when you increase the number of qubits. But it worked well for a small side circuit. On the other hand, we also have the tensor network simulator. Basically, you can simulate a larger system with some approximation. Basically, you truncate some of the feature within the circuit and try to keep the size of the representation of quantum state in polynomial size so that you can simulate a much larger circuit using tensor networks such as MPS or something else. On the other hand, for quantum error correction, we also have the Tableau simulator. Basically works for a subset of the circuit or called Clifford circuit by driving the stabilizer of a quantum error correction code. And for this type of simulator, I will characterize it accurate, but and also scalable because using the Tableau, you can simulate up to 10,000 physical qubits, but it doesn't work for arbitrary circuit. Like it's not universal because it only supports simulating Clifford and Pauli arrow, and in general, it doesn't support T. So can you go to the next step? So, as a matter of fact, then it might not be possible to find a classical simulator to satisfy all of the three requirements. Otherwise, we will not need a quantum computer. But we build tsim, which have the scalability and accuracy, but increase a little bit on the universality because it can simulate low magic error correction circuit. And I will briefly summarize how the Tableau simulator work because it's the background theory of the tsim and also the stim. So basically, when you simulate a Clifford state, you have to simulate track the Tableau or the stabilizer of a certain quantum state, where the stabilizer is just a tensor product of Pauli operators, where to represent the Pauli operator, you can just use x part to represent whether there's a exponent of or component of x operator and also the z operator. And in addition, you have a sign for representing the sign of the Pauli matrix. And in general, for n qubit state, we have need to specify an n qubit stabilizer state. We have to track the independent stabilizers as a tableau. So in general, Clifford gate will map Pauli to Pauli such that when driving the tableau, you can just convert the current Pauli tableau into another Pauli tableau based on the Clifford operation you are applying. And in addition, the computational basis measurement result can be inferred directly from the tableau we are tracking. So in that case, there are several early development of simulating quantum error correction using the Tableau, for example, from the earliest Gaussman approach, which achieve cubic complexity in terms of the number of physical qubit, and it later was optimized by Scott Arison using the destabilizer formalism, achieving quadratic complexity in quantum the number of physical qubits. However, if you want to use this Tableau simulation idea directly or naively in quantum error correction, then there are several issues because in quantum error correction, the circuit we want to simulate is actually noisy circuit, so that we have a lot of Pauli errors within the circuit. And using this naive Tableau simulator directly, we have to generate a lot of instance of this noisy circuit. For example, there's a X gate or X arrow on the second qubit for the first instance, and also for the second instance, we have to generate another. And each instance will requires one tableau, one different tableau to simulate the circuit. And using this approach naively, you will get quadratic or at least quadratic complexity in terms of number of physical qubits. But in quantum error correction, the number of physical qubits is relatively large. So actually, we don't want that. Is there any better way to do that? That's what STIM does. So in STIM, we kind of decompose this noisy circuit simulation problem into two parts. Firstly, we have the ideal circuit measurement result. Basically, we ignore all of the noisy effect within the circuit, then just focus on the ideal circuit by driving one reference tableau to get the reference measurement result from the tableau. And on the other hand, we have to handle those noise within the circuit. And in STIM, we focus on the effect of the noise in terms of the measurement. Basically, we track the error accumulation on the qubit so that by tracking the accumulation, we can predict which error will create some measurement flip by tracking the Pauli frame. So At very high level, we use the polyframe to only track the error accumulation. Well, basically, to track the error accumulation, we just need to track which poly operator are accumulated on each qubit, so that we only need 2n bits instead of a full tableau which scale quadratically. And for each sample, we just track different polyframe, and based on the polyframe, we can infer which measurement are flipped compared to the reference tableau. So by tracking the polyframe, we can get a different shot of quantum error correction measurement flips. And combining the ideal measurement and the measurement flip tracking from the polyframe, we can get the result or of the raw measurement result from each independent instance of quantum error correction circuit. So that's the basic idea of how STIM optimized the Tableau simulator in quantum error correction. Basically, STIM, people call it a flip simulator to just track the measurement flip using polyframes. And the complexity is pretty much better because we just need to do the ideal simulation once, which scale quadratically in quantum in number of physical qubits. And for the other part of the circuit, it is number of qubits independent because we just need to track the flips instead of simulating different tableau. And typically in quantum error correction, the number of shots is much larger than the measurement and larger than the number of physical qubits. And in tsim, we want to replace this methodology using the language of ZX calculus. Well, basically, I will abstract it as the error measurement map. Basically, you sample the error within the circuit, then apply the flip on the mirrors. And in STIM, it is tracked by polyframe and the frame update. And in tsim, we basically just need to use the ZX calculus to basically sample the error. Then using the ZX rewrite, we can figure out which error will flip which measurement results. And then by sampling the error, we will directly know the measurement result flipped caused by these errors. Okay. And in STIM, we support Clifford and Pauli arrow only. And in tsim, we can support more general arrows, including the non-Clifford gate or even coherent arrows. And here I will briefly give a high-level overview of the workflow of tsim, but it was covered by Rafael in his demo. So basically, you can write down your circuit, error correction circuit in different front end, including blockade screen and stim or circ or open chasm. Then you can compile the circuit down to a tsim intermediate representation, which is basically same as stim, but it supports non-Clifford gate, including T-gate and rotation gate. Then the compiled circuit will be compiled into parametrized ZX diagram. Then after simplifying the diagram, we'll get a much compact representation of the circuit we want to simulate. And then for each component, we compiled it into a JAX kernel, which represents the sampler as demonstrated by Rafael. Then from the sampler, we can get tons of measurement results or like many shots, like up to 10 to the 9 to 10 to the 12 shots very easily. And compared to other simulator, including Steam and tsim and recent developed the soft package, since tsim used the similar strategy as the flip simulator in Steam, so the Clifford sampling cost is actually number of qubit independent. And compared to Steam, it is universal and support arbitrary T-gate and rotation gate simulation. And moreover, similar to soft, we have the SIMD support and GPU support, which can further accelerate the computation in practice.
I have a
And
question.
as with, yeah.
So I wonder, when you're using this JAX, so you're referring to this high performance array computing, right?
Yeah.
And so this is done just on the processing side, or you're doing smart things about teleportation, like you're moving qubit around to parallelize those computation.
Basically, you just compile the simplified ZX diagram into a JAX kernel. So once you get the diagram, I will talk more details on the compilation later.
Thanks.
Yeah. So as mentioned by Rafael, we represent the Pauli arrows as parametrized spiders. Basically, you just represent different Pauli arrows as different variables within the ZX diagram without changing too much about the structure of the diagram. And then in that case, you can represent arbitrary noisy circuit in tsim for efficient Pauli simulation. And then after representing the diagram, we just simplify using the parametrized rules, including those well-known graph theoretical simplification rules, including local complementary and pivoting. And then we will get much compact simplified ZX diagram with smaller independent component. And then the only thing we need to handle is to generate some program to sample the measurement result from each component within the simplified ZX diagram. So the way we do that is actually autoregressive sampling. Basically, we focus each time we focus on one single qubit only, and trace out other measurement result. For example, there are many qubits. We focus on the probability of the first qubit being the zero state. And using this double ZX diagram representation, we can also represent this as ZX diagram. And after sampling the first qubit, we will assign the result of the first qubit to the second sampler, then simplify the second sampler and sample the second qubit, and so on. We get all of the qubit result from autoregressive sampling. So if the diagram is relatively small, then this autoregressive sampling will scale linearly as the number of bits in the subdiagram. And typically in quantum error correction, this is a constant, which doesn't increase as the system size. And then after constructing different autoregressive steps as diagrams, we have to decompose it into linear combination of Clifford diagram so that we can simplify it into a constant. And the way we decompose it currently is using the standard T decomposition, which basically decompose 4 T's into 7 terms, linear combination of 7 terms named BSS decomposition. And for arbitrary angle rotation, we decompose 5 rotation into 4 terms. And there are many other decompositions, such as the cutting decomposition, which basically can reduce the number of T terms based on the circuit structure we are simulating. And this step will become the bottleneck of the simulation. If you can find a decomposition which significantly reduce the number of terms you need to simulate, then the simulation time will be much faster. And for the complexity, I will just give a high-level overview on the complexity. Basically, we have the one-time compilation, which basically compile a circuit into a JAX kernel, allowing us to get as many samples as we want. And the compilation cost will be uh, um, well becomes just the autoregressive sampling and decomposition and the rewrite for all of the terms, which will definitely scale exponentially as we increase the number of T-gates, since the decomposition will in general give you exponential large number of components. However, for low magic state or low magic protocols, we consider simulating in quantum error correction, the number of decomposition is manageable. And on the other hand, we also have the sampling cost, which basically characterize the per shot cost for each shot we want to sample from the JAX kernel. And in typical quantum error correction simulation, the size of the decomposed component from the graph rewriting result or simplified ZX diagram is constant, and the number of arable or number of arrows is linear to the number of measurement. And we need many shots, but the number of measurement is like 10 to the 3 power of 3 and 10 to the 10 to the power of 4 number of measurement, but the number of physical qubits is at 100 to 1000, and the number of T-gate is less than 100. And combining all of the complexity together, in tsim, we achieve number of qubit independent sampling costs, while in soft package, which is recently developed by a Chinese group, they can only achieve qubit dependent complexity for sampling. And in the theoretical level, we believe tsim can outperform the soft package, but in practice, we do need a lot of optimization, such as the decomposition. Yeah, okay, I will hand over to Rafael on some of the benchmarks.
Yeah, thank you,
Yeah.
Chen. Yeah, that's the last part, but maybe if people want to ask question, otherwise we'll jump into benchmarks. Okay, I'll just go ahead, and that's just two more slides on some let's say somewhat preliminary benchmarks so far. The first one is the Clifford case, and you saw that in the notebook before, where tsim was able to outperform stim for some low noise level on Clifford simulations. And that's basically what you can see here. So blue is the stim baseline of time per shot, and here I'm just creating surface codes with ever increasing distance. And so yes, stim can be maybe even 2 orders of magnitude faster. I only plotted these p-values right here. At some point, tsim will be slower than stim. So it's a very special case for Clifford diagrams that have this. Well, for QEC circuits where Clifford diagrams have this very simple structure of ZX diagram, we actually don't need to perform any autoregressive sampling at all, but can just sample these F variables, and they will directly be related to my detector measurements. So yeah, stim has this cubic scaling, and actually tsim is slightly worse. And I think what's happening here is that I'm using auto tuning to adjust the batch size, basically as large as my memory allows. So the smaller the code, the more shots I can process in parallel. And so that gives me slightly better efficiency. And that worked into it. Overall, it looks like that I have a slightly higher scaling than N-cube, but that's just coming from the fact that my parallelization is a bit less efficient as I increase the circuit size. But so this is the relevant benchmark now for some non-Clifford circuits. And it's somewhat preliminary, but I took these circuits generated by Quizzix in the early stabilizer rank decomposition paper. So it's the first version of Quizzix here. So maybe it's not the most fair benchmark because there have been improvements since. But currently, in its current form, tsim is just using the BSS decomposition. And yes, you can do much better, and that's some follow-up work that we or maybe the community can do on this package. And so that's why I took the very first version of Quizzix and ran the same circuit in both Quizzix and tsim using our compiled approach. And I took fairly small circuits up to 20 T gates because that's really the regime we optimized for. And you can see, so each data point is one circuit, and I'm plotting the time it took with Quizzix and the time it took with tsim on each one axis. And already on CPU, we can see some major performance improvements, right? So reaching a 10,000x speed up factor. And this is all coming from that we are able to generate millions of shots at once. So there's some nice contiguous data structure, some nice parallelization. And especially in this regime, we don't have any ZX simplification overhead, which Quizzix has, because we moved that out into the compilation step. Here, I'm just showing the sampling time. So I'm completely ignoring the compilation step, which is a fair thing to do because that's a one-time cost that goes to zero in the number of infinite samples that I'm generating. And if I run tsim on GPU, all you have to do is install it with a pip installer with a CUDA 13 option and have a GPU connected. Then we see 1 to 2 magnitudes further improvements, and everything scales pretty much identical. And so this is with the circuits from the original Quizzix stabilizer rank paper without any noise. You might want to ask what happens if I put noise in there, and basically the result is not much happens. Everything looks basically identical. So there's almost no additional cost of including noise in the simulation, which is I think also expected from the considerations Chen made on scaling. So these are quite nice results, right? So you have 5 orders of magnitude improvement for some low magic circuits, and you can generate millions of samples, and depending on the circuit, really fast with this package. Yeah, and I should say everything's written in Python, so it's kind of built for collaboration. It's fairly straightforward to work with, and easy to collaborate on developing this package further. And also, it's not the last thing. I want to mention this amazing work by Kwok and collaborator on using this for some other circuits and making some significant improvements on top of Quizzix. On top of tsim. And so we had just released the package a couple of weeks ago, and already 2 weeks later, they updated their archive with some new simulation results based on tsim and some additional significant improvements they made on top of here. So overall, for this D = 3 cultivation circuits, they were like able to give another 140x performance throughput improvement on top of tsim, making this like a kind of the state of the art tool for this circuit. And so some of these optimizations, they work in general, and like we will work to implement or to fold this back into the tsim code base. Some of them are more specific to that specific circuit, but kind of the picture here is that it's tsim at its current form. It's an early release. It's definitely not the end of the story, and we're really excited to see that already there's kind of improvements happening on top of it, and that's maybe the idea that we can continue to improve onto it. Yeah. So as a summary, that's what tsim does. Move kind of that diagrammatic simplification overhead into the compilation step as a one-time cost by working with parametrized diagrams. And this was all developed as a technique by Matthew in this paper. And he also has a talk in a previous ZX seminar. So if you're interested, I encourage you to have a look and watch that talk as well. You'll learn much more details about essentially how tsim is doing the same thing. And the nice thing is that you get, this technique allows you to get Pauli noise basically for free included in your simulation, which is really important for the QC context. And then, yes, you want to sample detectors instead of measurements, just because error correction circuits are designed to have deterministic detectors, which give you very simple ZX diagrams and will give you much better scaling. And then the parallelization strategy should be over shots. There's different simulators. They all have different parallelization strategies, but in the tsim context or in the QEC context, you always want to be parallelizing over shots. That's the best and kind of most low-hanging fruit parallelization strategy that you have. So yeah, what are some things that we could go from here? It's a very early version, tsim. Definitely, we need more decomposition techniques. So the API of decomposing is very rudimentary, and there has been lots of work done already in the ZX community, also in terms of software. So some of these could be integrated into tsim, and Quark has done some amazing work on incorporating the cutting decomposition in there. Definitely, there's lots of options to improve performance of tsim. And currently, tsim is backed by a parametrized version of physics, which is basically also written by Matthew. I think that one could make some improvements, some improvements on that side, and that's currently just living on a fork under my GitHub. And also, one can work in more ZX reduction strategies, annealing for example, or various other strategies that are already used in the community. You could think about migrating to QuizX, considering ZH calculus for a better representation of Toffolies. And maybe there's also better stabilizer rank decompositions, especially since we always have to work with double diagrams to reflect traces and measurements. And from the Query perspective, we're a neutral atom company. Loss is a pretty predominant noise model. Currently, it's not possible to incorporate loss or leakage into these simulations without recompiling the diagram each time. So maybe there's something one could potentially think of. Yeah. So with that, yeah, we'd like to thank you for coming to this talk. Quera has a bunch of other open source projects. We have our compiler infrastructure. We have a whole compiler tool chain and various languages built on top of that. And now we have tsim as the simulation product. If you do like it, if you find it useful, if you use it in your work, yeah, please give us a star on GitHub. And yeah, we're open to pull requests and collaboration and discussions. Yeah, and yeah, hope you work with us or engage with this software package. Thank you.
Thank you so much, Rafael and Chen. Maybe since John is here, so he can moderate the Q&A now. I hope your connection is good.
Yeah, I can try, but if my internet is not working well, then yeah, we'll see. But yeah, thanks very much for the very nice presentation. I guess there were already lots of questions during the talk. I'll ask first, is there a
I caught most of the question. You're cutting out, John. But you're asking about whether there's a paper coming out. And yeah, we're working on a draft too, and we'll put out a paper hopefully fairly soon to also describe in more detail what all our improvements in the whole framework of tsim. Yeah, the code itself is open source already, right? So you can kind of understand everything from the code. There's also some extensive documentation. If you check on the GitHub, there's a link to our documentation, and there's some kind of QEC example and API use examples. But in terms of kind of describing the package under the hood, there will be a paper soon. Yeah.
Okay, great. I'm looking forward to seeing it. Yeah, are there any other questions in the audience?
Yes, I have a question. So I'm curious about the JAX kernel that is used to parallelize the computation. Is it used mostly in parallelizing over the noisy shots?
Yeah, it is used for two things. So it's used for noisy shots, because you're basically doing the same calculation over and over again all the time. But it's also used, and that was outlined in Matthew's paper, in the autoregressive sampling step. You have to build all these different ZX diagrams that trace out different qubits, right? Because you build diagrams that give you the margin and probability for the first qubit, for the second qubit, for the third qubit that you then sample from. And for example, if you look at a diagram like this one, it also has lots of parametrized vertices in here, where these M1s depend on your previous measurement of the qubit, and that will be different every shot as well, right? So this is the second kind of thing that always repeats. You have almost the same diagram, just different M values for your shots, and so that's also used for parallelizing over. So there's these two things, yeah. There's the noise configurations, and then there's the autoregressive sampling loop that we parallelize over these different configurations of polys.
Thank you.
So maybe a different question, because you have a very particular approach to how you decompose things and in which order you do things. I'm wondering, are there certain design choices where you tried something else and it turned out to work a lot less well, and you sort of settle on this one's the best place?
Uh-huh. So what did not work? I guess, yeah, one thing I can mention is that whenever you you have one thing to consider is that whenever you have a diagram like this and you have a large QEC circuit, you have thousands and thousands of different error variables, right? Because every gate gives you another error variable, right? So one key insight is that once you simplify, this actually reduces to just a few independent variables, right? So if you wanted to track all of these E variables, initially that's what I tried, everything became horribly slow, and it's not kind of a feasible approach, right? But simplifying the ZX diagram essentially turns these E variables in error mechanisms in kind of the language of stim and QEC, and these are much less. So I mean, in Clifford diagrams, it even just turns into detector flips and observable flips, and so you get a much smaller set of variables that you need to track. And so I think, yeah, here that was really important, doing some strategies to kind of reduce the number of Boolean variables that you need to track, and that you also need to evaluate your diagram. Yeah, it's maybe a bit detailed. I hope it makes sense. Yeah. Oh, you're muted, John.
Why? Can you hear me?
Yeah.
Not sure if my mic's working. Okay, yeah. Zoom is not showing that I'm talking. So you're using the 6 to 7 T-gate decomposition, right? The DSS decomposition. But there's also the 5 into 4 decomposition, or the 4 into 5 decomposition, which is like the team. Well, it's a one from like a newer paper by Alex Mier, which has like a better asymptotic scaling. I was also wondering, because you're using this parameter ZX from Matthew, but that's using the cut decompositions, if I'm not mistaken. But then, are you using the cut decomposition?
Yeah. So far, in fact, yeah, for T's, we just use that 6 to 7 BSS decomposition. And it's not the best, right? Yeah. It's just we didn't get around to implement that yet. So we can improve easily on all of these results just by doing that. We use this 5 to 4 one for arbitrary rotation gates. I don't think this one has really been used so much, but it's also from the literature for arbitrary rotations, because yeah, that's also used. Some of our use cases are arbitrary rotations. But for example, that follow-up work by Kwok, they used cutting decomposition, and that is giving much better results than any of these decompositions. So I think my intuition is that depending on the structure of your circuits, where different strategies can work significantly better than other ones. And in particular, I guess Kwok showed in their work on cutting decomposition, that can give you a very low rank of the whole circuit. So I think the idea would be to kind of build out a much better decomposer API. And yeah, just we didn't get around to it yet, but if we would love if people want to help us out here, because there's been so much work being done on finding better decompositions in the community. Would be nice to kind of integrate that all into tsim.
So would this, for instance, be a trade-off between doing more pre-processing time, trying to use absolutely the best decomposition for a particular circuit? Yeah. See.
Yeah. I see Matthew has his hand up.
So, thank you for your talk. It's a very nice talk. Can you hear me okay?
Yep.
I just wanted to ask about the benchmark slides you had near the end. Yeah, that one specifically. So what is the difference in the types of graphs that we see on the bottom left, where you get a speed up of 100,000 times, versus the type of graphs at the top right, where you get 100 times speed up? Is this just related to the scale of the graph?
Yeah, it's just the depth of the graph. Yeah.
Okay.
Yeah.
But in general, then it's just the improvement is stronger when the graphs are smaller.
Yeah. And one reason I think is that you don't have that ZX full reduce overhead that Quizzix always has, right? So that's cubic, and especially at these small graphs, that one is the dominating factor. And so you don't have that at all because you've done it previously in the compilation step. And so that gives you massive speed up there. And also parallelization works best, or works really well, because you kind of, huge array sizes that yeah, and yeah.
Yeah, that makes sense. Thank you.
So regarding this pre-processing of your ZX diagrams, you're looking for different decomposition techniques for different families of quantum circuits. Have you noticed if you decompose a diagram in different ways, the noise simulation will give you very different results, and maybe some of them will have suppressed error rate because you've done something very smartly?
I guess the decomposition shouldn't affect the simulation result. It can affect the simulation speed, but not the measurement shot distribution, since the decomposition is always exact. But there is one direction we haven't explored yet, is the approximate decomposition. So probably we can explore that in the future.
Thank you.
Hi, I have like a question. So in some of the simulations where you replace like T gates with S gates, like so in some cases, like some of these distillation numerical experiments, you can replace it with an S gate. Um, have you seen like I don't know if you actually ran like error analysis on that, but do you think that there's a different error realization would lead to a failure in the S case versus the T case, for example? So like because you have access to the actual errors applied now. Do you think that that would be like a good study, for example? Like, so what types of error realization leads to a true logical failure without replacing like T for S or whatever other proxies?
That's a good question. My intuition is that for those circuit with T gate we have, since T will convert Pauli to Clifford, effectively at the measurement level, it will create superposition of Pauli arrows. And probably the superposition of Pauli arrows will be combined to other superposition, which will eventually give you higher logical error rate. But at the very low level, I don't have the instance of such a example.
Thank you. Thank you.
And there's related work to that, right? For certain circuits, Pauli's will commute to Clifford's at the very end. That's another simulation strategy, right? Because you can just take your pure circuit that doesn't have any noise, and that one has a very low rank, right? In the case of a magic state, just rank 2. And then if you know how your Pauli's propagate to Clifford's in the very end, you can now do a Clifford simulations on each of those two branches of your rank decomposition if you do it that way, right? But that assumes that you always have Pauli's that nicely propagate to some Cliffords.
So in the paper by Shruti Puri's group, like the folded cultivation paper, they used a different way. I'm not very aware how it works, but they use a different way of sort of doing exact simulations. So I don't know if you understood that method, and if it applies to like if it's worthwhile to integrate that as well, because they seem to be able to do an exact simulation by some hybrid approach of ZX and stim.
Yeah,
Like,
I mean that approach requires so basically all of the cultivation approach is built based on the fact that T state is a eigenstate of the SH gate or some of the S gate on the on some basis, and we are going to measure the parity of that logical operator using the physical circuit, and the way they implement that measurement is based on the fact that the surface code has a full transversal that gate, but in the color code it's just fully transversal, but in surface code it's the full transversal version. So in their implementation, they need the transversal CCD gate for that part. Not sorry, not the transversal CCD, but the physical CCD gate. But it's kind of tricky to implement that in tsim currently because in ZX there's no native representation for CCD gate.
I see. So it's this ZH stuff that it's
Yeah.
probably worthwhile. Okay. Okay. Thank you.